Multiple linear regression. The multiple regression model looks very similar to the simple regression model, except of course, there's more than one x. And we separate out simple versus multiple just for ease of education. It's easier to talk about one x, it's easier to understand how it's fit than when we go to multiple regression. But there's nothing really that different from multiple than simple, except for interpretation, as we'll talk about in 1 second. So what's the deal with multiple regression? Well, we have multiple x's. We actually usually use the letter k to say we have k explanatory variables, sometimes called independent variables, sometimes called factors, and they're used to explain the y variable. Again, we have noise in the model, and you have a bunch of x variables used to explain y. The only thing different is interpretation, and we'll talk about that rather quickly right now. So suppose we have a data set on 15 randomly selected houses, and our y variable is the price, and we have size, and the units are weird. The size is in 100 square feet, age is in years, lot size is in 1,000 square feet. We get the output. So this is how you fit a multiple regression model in R. LM for linear model. You give it the y variable, and then you just go and say x1 plus x2 plus x3. In this case, if there are more x's, just add them on. You get the output here. You get r squared and now adjusted r squared, and they differ. Adjusted r squared is adjusted for the number of x's in the model. It's the better one to look at. And look how it's a little bit lower here. If we go through here, what these stars are telling us in each p-value here, we ignore the intercept for the most part. We want to know how the x's relate to the y. The intercept comes along for the ride. The intercept is the value of y when all the x's are 0, which in general can't happen in practice. So the intercept is just coming along for the ride. We usually keep it in and we ignore it. But what we're seeing here is what's being tested under the p-values. P-values always go with the hypothesis test. Is in generality, we're testing does beta I equal 0, and the alternative hypothesis is beta I not equal to 0. So individually, by itself, we would say we need size in the model. We're going to reject it 0. It doesn't look like it's 0, so we need size. We don't need age. We need lot size. And what you're seeing from the r squared being a little bit higher than the adjusted r squared, that tells you probably have some stuff in the model that you could remove. If we were doing model building, we'd remove age, refit the model, make sure all the resulting p-values are less than 0.05 on the x variables, and that'd be the model refit. So individually, you can go down here and determine what you need, what you don't need. Essentially, if you see stars on the right-hand side, you need it in the model. That means you're going to reject that the coefficient's 0. It's not 0. You need it in the model. If you don't see stars, you don't need it in the model. The way hypothesis testing works, though, you're only allowed to drop one at a time. And we'll talk about that in a model building video. But it gives you an idea of what you need and don't need in terms of p-values. But you're only allowed to drop one at a time, refit, drop another one, refit, so on and so forth. Multiple regression also gives you the F statistic, which is at the very bottom here, and it's this thing. This is a really weird statistic. A lot of stuff can be messed up in regression. If your x's are highly correlated with one another, you sometimes can get weird output. The F statistic at the very bottom is concrete. Very good statistic. It's not that useful statistic, but it's a very good statistic in that it often cannot get messed up. And this is testing the hypothesis that beta 1 equals beta 2 equals beta 3 equals 0. And you're thinking, what is that? It's called the overall F test. And it's testing at the same time does beta 1 equal beta 2 equal beta 3 equals 0. If that were true, yeah, we're not supposed to say no hypotheses are true, but if that were true, you need nothing in the model. Your x's have no explanatory power. The alternative hypothesis to this is you need at least one x. Which one? You don't know, but you need at least one x. You can see why it's a crazy test, because if you fail to reject, there's some structural issue with your regression model. You want to go back to your x's and examine them. They might be highly correlated with each other. Something really weird is going on. You always want to see a small p-value here. You always want to be rejecting this null hypothesis. If you're not rejecting that null hypothesis, something really weird is going on in your regression. Because that null hypothesis says you don't need anything in the model, and you want to be rejecting that. So of course here, really small p-value, we're rejecting it. We need at least 1x in the model. We look up, we need size and lot size, so it's clear. But it's something we look at, and we're always, 99 out of 100 times, you're always going to see a small p-value there. If you see a large p-value down here, something really weird is going on. Now the other thing we want to be able to do, sorry, I went ahead just too quickly, is how do you interpret this? And the way we interpret these in multiple regression is keeping everything else constant. So what is the effect of size on price of the house? As size goes up by 1 unit, the price of the house goes up by $4,000, everything else being held constant. Because there are other variables in the model, you have to say what happens to them. You just say, I have 2 houses, they have the same age, they have the same lot size. One size is a little bit bigger than the other. This is how the effect on price works. What's the effect of age on price? Well, as age goes up by 1 unit, which is years in this case, as age goes up by 1 year, size and lot size held constant, price goes down by $236. As lot size goes up by 1 unit, price goes up by $4,000, everything else being held constant. So that's the only caveat when you do multiple regression. When you want to talk about the effect of one variable on the y, you have to put in that phrase, everything else in the model held constant, which makes sense. You're changing one variable. What would you do with the other ones? You'd hold them constant. So that's the caveat when you interpret multiple regression. The other reason we do multiple regression is to get better predictions. It's get better explanatory power by using more x's. As an example, we have Zagat food ratings for Manhattan, and we have data on price of meal, and then we have the ratings, food quality, decor, and service. And these are all on 1 to 30 scales. This is a 1 to 30, and this is 1 to 30, and this is 1 to 30. And we're trying to predict the price of a meal, that's the y variable, based on these 3 explanatory variables. So we have price versus food, price versus decor, and price versus service. If you had to pick one variable, which variable seems to be the best one? What do you think? Maybe service or decor? But you could run the one variable regression models and see which one would give you the best explanatory variable as a single variable. Let's check out price on food quality. So we're going to regress price on food, and this says we need it in the model. Now, R squared, look at that, it's really low values of R squared. And let's do predictions. Let's look at our S sub B here. This is our S sub B value. So this means if we do predictions, our predictions are going to be plus or minus approximately 2 S sub B, plus or minus $24. And these meals range from 0 to 80. That seems like a lot, but we're going to do predictions. So if we have food quality and we're going to do predictions, we're going to be plus or minus $24 in our predictions. How do we interpret this? This says you really need food in the model. There is a relationship between food and price. And this says for each additional food score, as food goes up by 1 unit, the price of the meal goes up by $1.64. But there really is a positive relationship between food and price. But look at the R squared and look at how big this is. There is a relationship, but it's not that good. Let's now do the multiple regression. So we're going to add food, decor, and service. Now, what's interesting is now when you add everything in the model, do you need food? No, no stars. You don't need food. Do you need decor? Yeah. Do you need service? Yeah. Let's go back. You don't need food. So what happened? Well, how's this? Now our S sub B is 9.7. And plus or minus 2 S sub B is going to do, oh, no one said there's going to be math today. That's a 19.4. And 19.4 is less than 24. So what do you see happening? R squared went up. R squared was 0.0683, goes up to 0.424. We don't care about that. Whenever you add x's to a model, R squared goes up automatically. That's not fair. We want to look at R squared adjusted. It went from 0.0635 to 0.415. So R squared adjusted went up. That's good. S sub E went down. That's good. This means we're explaining more variation and our predictions are tighter. We're getting much better predictions. And so instead of being plus or minus 24, we're now plus or minus 19.4. And this is the whole idea of multiple regression. The whole idea of multiple regression is, can you find a combination of x's that give you good predictions? It's nothing contradictory. Is food related to price? Absolutely. Is it a good predictor? Not so much, but it is related. If all you had was food, you'd use food. It is related to price. However, once you have decor and service, this is actually very sad from a person that eats out. It says decor and service are all you care about. Food does not actually affect the price. It's decor and service. So it says once you have decor and service, they explain enough. They explain a great job, actually. You don't need food in the model. So you would drop food, refit. These probably would stay significant. And then that would be the model you use for predictions and your report. So once you have decor and service in the model, food is not needed. And what are we trying to do? We're trying to explain why to the best of our abilities. And what that means is we want S of B to be as low as possible using as few X's as possible. And that's what we have here. We now have a model with two X variables, and we reduced S of B by quite a lot.